Light shafts form an interesting phenomenon that can significantly influence the mood of a 3D scene, both when subtle or more prominent. They are caused by the single scattering of light in thin participating media, such as air. We aim at giving artists a global, high-level control to stylize this single scattering interactively. To do so, we propose two stylization concepts. First, we enable artists to modify the complexity and shape of the light shaft appearance by interactively manipulating the shadow map. Second, we enable a light shaft stylization through transfer functions that artists can edit in our interactive editor. In some cases, the user may want a more simplified appearance of the light shafts. To do this, we apply a hole filling process on the shadow map. This is done by a closure operation and effectively decreases the complexity of the scattering effect. We propose a method to enhance the silhouette of objects. In this case, we perform an extrusion of the object along the view ray, which boils down to a one-dimensional epipolar dilation of the shadow map. While this dilation also fills holes, it produces an enhanced object silhouette and results in a somewhat more drastic appearance. In other cases, an artist may want to increase the scattering appearance complexity. This can be achieved by adding small light shafts. We do this by creating holes in the shadow map with the aid of a thresholded Perlin noise map. Animating the noise can produce some interesting results, like the illusion of leaves moving in the wind. It can also simulate the appearance of motion. Because we create artificial holes, one may expect artifacts when looking directly into the light source. However, for complex objects such as this tree, the scattering still looks plausible, because the physically correct results are hard to predict. One may also expect problems for animated light sources, as we create the holes purely in the 2D space of the shadow map. In this example, the holes are fixed during the light animation. Nonetheless, inconsistencies are not perceivable. Finally, we introduce transfer functions, which are defined by a 2D texture and map properties of a view ray to a scattering color. For every pixel and its underlying view ray, we evaluate these properties and use the transfer function to obtain the scattering color. This allows for global control over the scene atmosphere and enables artists to transfer atmospheres from one scene to the next. These transfer functions can be modified using our interactive editor, where layers can be defined and blended. The user can also select pixels in the scene and modify the transfer function at the location corresponding to this pixel. This changes the scattering appearance of pixels with similar properties, in this case average visibility and the depth. If the user wants to modify a certain point in world space, simply tracking the camera updates the transfer function so that the point is always influenced by the modification, regardless of the camera position. Finally, transfer functions may also be blended in an animation, where we support both static and dynamic cameras. Since our technique works in real time and supports dynamic scenes, we imagine that animated transfer functions can be especially useful for stylizing scattering in in-game cutscenes.